schools might have to buy my calculator and I like it's become a hot commodity for all my friends who are in chemistry and don't have big calculators. Like I'm not using it. You want to borrow it because you can actually see the screen.
That's it. Anyone that's looking to doesn't need it is just gonna give it away. I'll take them.
I think it's next year for chemistry. Even if I can't do the tests, then I'll do the homework. I mean, the screen. I like having the big screen. Oh, I'm gonna give you a high five. I'm at that point to where like it says a quarter battery in it. I got that today.
Yeah. I've got an old school TI-85.
My priest, like this Sunday, he was like,
I think you can put them face each other and you can transfer data through infrared. I think that's the only way. It doesn't even like plug into the computer. All right. Let's get this going. All right, so pairwise.t.test. It works. It's easy. If you're doing Welch's t-test, do list, you just have to remember the switch. So pairwise t.test will run pairwise test, pairwise t-test on your data. R will automatically separate your data by groups and run each test. It will also adjust your p-values based on your method of choice.
So
all right.
Question, do we have to run two keys or can we just do this when it's saying equals true?
We'll talk about that.
Okay. I was thinking about it earlier.
All right, so our code is pairwise.t.test, our measurement variable. I'm going to say, actually, we'll do this. Y, comma, x. No, we can't do it. Data $y, data $x. Let's make it clear since you're mostly going to be working with the data frame. So data $y, data $x, p.adjust.method, and then pool.sd. All right, so data $y, that's our measurement variable. That's our dependent variable. Data $x, that is our categorical or grouping variable. So this has to be a group. All right, this has to be nominal. Could be ordinal, since ordinal is also qualitative. All right, just misspelled that. p.adjust.method equals bond. This will do. This will apply Bonferroni adjustment to the p-values. Use Holm if you want Holm adjustment or the method of Holm. All right, and then pool.sd equals f. This is run Welch's t-test. Set to t if you want regular t-test. All right. So did you get that? Question. Can we use this method instead of 2 keys? So we'll say if all assumptions are met, if all assumptions of ANOVA are met, then can you use this method instead of 2-key HSD? So that's going to be our question. I'm going to go to this ANOVA assumptions are met. All right, so let me load. So we worked on this data set. How do I load it? Here we go. Plant growth. All right, so we've got plant growth, right? When we did plant growth data set, all assumptions are met. Library car, let me load the car package. All right, car package is loaded. Let me run that. All right, so let's take a look at it. We ran 2 keys here. Actually, let's compare plant growth analysis. So C, assumptions met. Actually, this is ANOVA, assumption met. So we have this. All right, so, whoops, darn it. So we're going to do mod 1. We fit our data, which was in plant growth. Let's just copy this. So 2-key HSD of AOV of mod 1. So we already knew that it was ANOVA was significant, and we get these p-values. Here's 2 keys. That's 2 keys output, and we're going to look at our p-value. Here's the pairwise. Here's a pairwise t-test output. So we'll use pairwise.t.test. Our grouping our measurement variable is this plant growth $, weight, and then our grouping variable is plant growth $, group. All right, we'll do p.adjust method. We'll use Bonferroni. And we want pool.sd equals t. And we can see p-values on both. What you're going to see is that the p-values differ. They differ. The p-values for the Bonferroni adjustment are going to be a little bit higher. So we had 0.39 versus 0.58, 0.198 versus 0.263, 0.012 versus 0.013. Well, Bonferroni is conservative, so our p-values will likely be a little bit higher. What if we used method of Holm? Method of Holm, we get different p-values. In this case, we get lower p-values when we have large values, but the significant terms still remain significant. So in the end, our conclusions basically stay the same. So we had a difference between treatment 1 and treatment 2. All right, that was our one difference. 2 keys found that. And Bonferroni and Holm adjustment also found that. Could we use it? Yes, we can. Is it preferred? Not really. So yes, so we'll actually say this. P-values differed with our adjustment method, but our overall conclusion remains the same. Remains the same, which is that the only difference is between TRT1 and TRT2. All right? So, can we use this method as a post hoc test? Yes, we can. Is this method preferred? No, it's not preferred. And the reason it's not preferred is we lose power to detect it. Tukey HSD is around because it takes our variances and comes up with like a population level variance, which increases our power. So it not only does like a total population, but it also tends to account for the individual variation within the groups. When we use this pair dot or the pool dot SD equals T, it makes assumptions that all variances are equal and uses that to calculate all of our p-values. Also, the Bonferroni adjustment takes our p-values and just adjusts where our critical values are. Tukey's doesn't do that. Tukey's does all of it at once. So overall, the Tukey's remains at 0.05. So anytime you do something extra to the data, you're going to lose value. So how do we kind of verbalize this to get this into words? Tukey HSD doesn't need to adjust the p-values because it's overall or family-wise type 1 error rate is already at 0.05. Thus, Tukey HSD is more powerful at detecting differences than pairwise t-tests and then pairwise t-tests with p-value adjustment. So we lose power when we do this method, but we're going to be okay with that because when we have unequal variances, we're doing a method that is easy and it has a little less power, but it's easy. It's easy. So, could we do it? Yes. Is it preferred? No, it's not. And it's tied to how you control for that type 1 error rate. Tukey HSD accomplishes that using its standard error calculation. All right. Still working? That's a good question. Kind of assumed it would have come up. All right, we good? All right. I am going to scroll all the way up here. Right up to Anova review. Delete it. I'm going to resave. So now we are on assumptions violated part 2, and I didn't get one of these put together, but that's okay because I think that first one was a major write-up. Not R&D. All right. Violating normality. All right, so the data set that we're going to work with is, find it, posted those folder. I think it's flower. I do, I think it's flower. Yep, all right. So go ahead and import flower data set. Put it on it here. Heading, yes, strings as factors, yes. And you need the car library, if you don't already have that. All right, violating normality. Data is flower.csv. All right, so in this data set, is that we have flowers that vary in color. All right, so flowers vary in color. During one growing season, we harvested seeds and determined the number that survived to maturity. I should say that germinated and survived to maturity. All right. So our question does flower color affect survival of the offspring? So does flower color affect survival of the offspring? So if we look at our data set, we can see that it's two variables, flower and survive. All right, we can see that color has 4 levels, and survive looks like it's numeric. All right, so the first thing we do is just kind of take a look at the data. So I'm going to issue the plot command. So obviously survive is our measurement variable. We measured how many of our seeds survived. And what you can think of is that each flower produced a different number of seeds, or maybe we'll say that each flower produced the same number of seeds. We germinated all of them, grew them up, and counted how many of those seeds actually grew and survived to maturity, for them to actually set flowers themselves. So we're going to use survive as a function of color. Our data is flower. It's in our data set. And we get something like this. Observations. Based on our figure, what's one observation that you can make about these data?
An error saying that survive is not found.
Oh, use $sign. Squiggly. All right, what's one observation that you can make from this data set?
Blue has an outline that's kind of laid out there.
Okay, so we might have some outliers. Okay, I'll take that.
So then, perhaps if it's shoving the rest of it down, it's got the water. Why do you have to do that?
Okay, so what was the other part?
It's kind of like pressed down.
Okay, okay. Could we say
I don't know how to describe that.
skewed?
There we go.
So compressed, skewed. And we're going to clarify and say that we're compressed, and when we have skewed data, we're bounded by 0. So we can't go below 0 because you can't have negative survival, right? So we're bounded by a number, and this is one of these things where anytime you collect data and you're bounded by a value, you can't be lower, you can't be higher than a certain value. You're gonna get figures that kind of look like this because we can't go the opposite way. If, however, I made a figure and I've got my standard error bars going below zero, warning bells. Warning bells should go off. All right, you can't have that. All right, compressed skewed data. What else? Anything else?
I would say like all of the boxes overlap one another.
Okay. So maybe no difference in means or medians. So we have overlap. All right, and I'm going to say the compressed and skewed data, look at the medians. They should be in the middle of our boxes. We've got these that are kind of right near the bottom of those interquartile ranges. All right, so we kind of have preliminary observations from these data, so hopefully we're not surprised when we run any of our analyses. So we have two variables. One's a measurement, one's a categorical. We're interested in comparing the mean survival between our flowers because that's what our question is. Right? Does flower color affect survival of the offspring, which means our null hypothesis that we're going to test is that the mean survival is equal across the colors, and then the alternate is that mean survival differs across the colors, right? So we've got like a preliminary observation just from this box and whiskers plot. All right. So let's go ahead and check our assumptions. All right, so go ahead and check the assumptions. And I'll break this down to normality. Oops, not to normality. Interpretation. And then homoscedasticity. Do interpretation. All right, so go ahead and do that. This done over on mine. All right, did you get it? All right, so we check normality, use QQ-plot. We can always take subsets if we wanted to get these bigger, but I can see two main points. One, I can see our individual numbers. And remember why I said they appear like this? You can see all the points line up in a row, kind of like steps. Remember why they appear like that? So these are whole numbers, right? It's discrete, and we've got replicates. Anytime we have a lot of replicates in our data set, that could be because they're discrete or because of rounding, you're going to see the points line up on the same line. So we've got discrete data. No big worries, though. But the other thing is that it does look like we're curved. It looks like we've got this curvature going like this. This one less extreme, but I think the curvature is still there. I think there's curvature in all of them. So my interpretation here, data are probably non-normal. All right, I'm going to say probably because I still think with the discrete data, it's going to be hard to really say definitively. The more data points you have, the smaller that 95% confidence envelope will be, and then you're going to have all of those same values start to expand. Like this point here, you see this range right here. I mean, you're going to have points outside on that end and points outside on that end, and that can happen, especially in the middle. But I think the curvature is suggesting that we're non-normal. So we still have to check equal variances. So for this, I ran Fligner-Colleen test. So homoscedasticity, remember, data are likely non-normal. So we should use Fligner-Colleen test. But here, Fligner-Colleen test appears to have equal variances. So variances are equal. We're going to say Fligner-Colleen. We've got our chi-squared. So x squared is 0.65. df is 3. And p-value is 0.89. Around that. All right. So data are non-normal within each group, but the variances are equal. We have three options. Oh, geez, man. All right, we have three options. Run ANOVA as usual. And the reason being, ANOVA is robust to this violation. Meaning that we're going to likely get the same result. We're going to likely get the same result from this test as if we choose another test. All right. Second option, run a Kruskal-Wallis test. This is a non-parametric test of medians. And our third option is Permutational Anova. I think we'll leave it at that.
That's the one that you'll learn.
We're going to learn how to do that. That'll be next week. All right. So first off, go ahead and run the regular ANOVA, and if you get a difference, let's go ahead and run a Tukey's just to see what we get. Give you a few minutes to do this. Oh, it's okay. So I think we've got the options listed on the other one as well, but this is part 2, so we're gonna rehash it. Run a regular ANOVA and then post hoc Tukey's. We need it. Guess I'll be on 2. Guess I better get the aggregate function on here. White. Green. Blue. Red. All right, did you get it? So ANOVA tells us that we have a difference. All right, so difference in survival exists between the colors. We would then do a post hoc test. And I'm gonna mark this as being not correct. The ANOVA is fine. ANOVA is robust to violations. Post hoc test, Tukey's, isn't. But there's a catch, and we'll get to that. But the reason we're doing this is we want to compare our answers to the other 2 that we're going to be doing. So Kruskal-Wallis and Permutational Anovas. So here's our Tukey's. I get it, so that basically the only difference that we observe is between our 2 extremes, between the white flowers and the red flowers. Those are our differences. All of the other comparisons are not different. So white, green, and blue are all similar. Green, blue, and red are all similar. It's just the white and the red. All right? But we're going to add a note. Tukey's is not robust to violations of normality. Thus, despite being able to use an ANOVA when we violate normality, we really can't utilize Tukey's as a post hoc test, which kind of then begs the question, what can we run? Well, our result would be a randomization test of some sort. If we're going to use a randomization test, why not just start with a randomization test? That's only part of the answer. So our option is to utilize pairwise permutational t-test with p-value adjustment. However, if the non-normality is skew and all groups exhibit the same type of skew, the same skew, so all groups are skewed right or all groups are skewed left and about the same amount, then we can probably get by with 2 keys, 2 key HSD. So that's kind of the exception. So t-test and ANOVA, if you violate equal variances, they're bad. Don't use them. If you violate normality of ANOVA, that's okay. ANOVA is robust against that. If you violate normality while running a t-test, you can still run a t-test if the non-normality is skew and both groups exhibit the same type of skew. So if we had 2 groups that we're comparing and our data points look something like this, that's okay to compare the means because our underlying data are basically the same type of distribution. It would be a relevant comparison to compare the means between these groups. All right, so we can compare these, but if we had a third group that looked something like this, and we try to compare the means, now we've got a problem because we're no longer in the same direction of our skew. We've got 2 different distributions, and any result that we get that says the means are different or they're not different is just going to be wrong. So the same type of thing happens with 2 key HSD. If they're skewed, and if we're skewed in the same direction by about the same amount, it's usually going to be okay. All right? My recommendation, you can do it. You can do ANOVA. Best case scenario is that p-value is greater than 0.05, and then you don't have to run a 2 keys. It's the best scenario. But what happens if you choose not to do that? Or you run an ANOVA and your advisor or a reviewer looks at you and says, well, you can't run ANOVA because you're non-normal. What do you do? One option is the Kruskal-Wallis Test. All right, Kruskal-Wallis Test is a non-parametric version of ANOVA. What it will do is that it ranks the data. So ranking of the data is putting them in order from smallest to largest, and assigns a number for our ranks. All right, so the smallest gets 1, our largest value gets however many values we have. That's the largest number. So it's going to rank the data and then compares the average rank between the groups. And it does so using an ANOVA. Which is kind of interesting. So you took your data, which was actual measurement data, and change it to a rank of numbers. So you can have a variance because your average rank is basically going to be your median value. And then you've got number of points away from that median value that you can calculate your variances. All right? So because of what we're doing, our null hypothesis is that the medians of the groups are equal. Since we're converting to a rank, we've lost the actual value of the mean, and when we take the average of the ranks, we're actually looking at the medians. So median of the groups are equal. Our alternate is that the medians, at least one median is different. Let's do that. At least one median is different from the rest. The assumptions. This test has assumptions, which is, I mean, other than the fact that we're comparing medians and not means, I mean, that's a big negative if we're interested in means. The other is the assumption. All right, so the assumption, two assumptions. So number one is that the data have the same general distribution within each group. Distribution of y's between each group, or in each group. So that means if we're skewed right, all of the groups are skewed right. If we're skewed left, all of them are skewed left. If we're leptokurtic, so peaked, we're leptokurtic in all of the groups. All right? And that's somewhat standard. If we're non-normal, we're usually going to satisfy this assumption. But the other one is that our variances are equal. This one's going to be a little bit harder. This is going to be a little bit harder to satisfy. But it can be satisfied, just like the flower data set. We've satisfied that. Did we satisfy the same general distribution in each group? Yeah, we kind of did. So based on our QQ plot, you can see we tend to be curved up. So in our QQ plots, they have the same general pattern. I'd say we have the same general distribution. So our assumptions, we're going to say, are met for this data set. All right. Our test statistic is a chi-squared value. So chi-squared, which means we have degrees of freedom. All right. So reporting then requires us to report the conclusion interpretation, the test statistic, degrees of freedom, and our p-value. So it has all five. Our R code is actually really easy. It's Kruskal-Test. And we can write it as a formula, as we have been writing things. All right, so flower data set. Let's run a Kruskal-Wallis test on this. So it's Kruskal.test. We are testing survive as a function of color. The data is found in the flower data set. Again, this one. So what's our conclusion? What's that? Yep. Yep. Look up. I don't think this is. Yeah, we do. All right. So, yes, our write-up for this case is that survival varies by color. But we should probably specify median survival varies by color because we're testing the medians now instead of the mean. Kruskal-Wallis, we've got our chi-square test, so 15.72, go to 2 decimal places for our test statistics. We report our degrees of freedom, and our p-value is 0.0001. All right. So, what do we do now? Well, we have a difference. We don't know which groups are different. So now we have to figure out which ones do actually differ. What do we do? So, we know a difference exists, and medians exist. So now, we have to determine which groups differ in their median. Our only option is to run pairwise tests with a p-value adjustment. All right, that's going to be our only option. I'm going to move this over because we do, like we had a t-test and then we had Welch's t-test. Or we have ANOVA, and then we have, basically said, if we had two groups for an ANOVA, it defaults down to a t-test. Well, there's kind of an equivalent called Wilcoxon rank sum test. All right, and that's kind of like the equivalent of Kruskal-Wallis with two groups. All right, and we could kind of do it the same way. We can use, instead of pairwise.t.test, we would use pairwise.wilcox.test. All right, and we give it the x, we give it the g, we give it the p-adjust method. We don't worry about pool.st because it doesn't need it. It doesn't take it. It compares, it will compare our medians. So what we can do is go ahead and run that. So we can run pairwise Wilcoxon rank sum test with p-value adjustment. This test is a two-sample test equivalent to a t-test of the means. And I'm going to put in parentheses, just like the Kruskal-Wallis versus ANOVA comparison. All right, so kind of a two-sample comparison test. Our R code for this is pairwise.wilcox.test, where we give it data $y, data $x, and then p.adjust.method, and whatever method we want, or p.adjust. I don't think we need, p.adjust.method. All right, where it's going to be Bonferroni or whatever, Bonferroni or Holton. Reporting for this is going to be just like for Tukey. All right, so we have to give the conclusion interpretation. We have to give the p-value adjustment method, and we have to give it what test was run. So pairwise Wilcoxon rank sum test with this type of p-value adjustment, and then adjusted p-values, or p-adj, and adj would be in our subscripts. All right, so for our flower data, all right, we would just write it out as if we were doing the pairwise t-test, but update the actual test. It's a Wilcox.test. So flower $survive, comma, flower $color, Then P dot adjust method is, I'll use Bonferroni or home. Actually, we'll use home, since we have an example of Bonferroni. And we get all of our p-values.
I think that all these tests are named after someone's last name,
Mm-hmm.
which is why they're.
Kruskal-Wallis named after you. Yeah. So this is the Pairwise Wilcoxon test. All right. So we've already kind of did the write-up where it was like data appeared non-normal, variances are equal. We run a Kruskal-Wallis test. We have a difference. Now we have the write-up for this part, which kind of goes back to, okay, what's our aggregate, right? What are our averages? But we're not comparing averages. We're going to need the medians. So let's use the aggregate function to pull those. And this is the great thing about the aggregate function, is that we pass it any sort of value that we want, and it tells us that we have white, green, blue, and red. So I'm going to abbreviate it. Those in order. And you can see white and green have the same median. We've lost information when we converted things to rank. That's why we lost power. All right, so now I'm going to look at my adjustment method. So white and blue are different. That's what I get. White and green is not. White and red is different. Green is not accurate, but different. So I think that's our comparison. So now we just verbalize it. So with our write-up, we figured out which ones are different. I think it's clear enough to say that we can say pairwise Wilcoxon rank sum test with home p-value adjustments. What would be the best way, simplest way to say this? And white is different from blue and red. So white and green form a group, and green, blue, and red form a group, basically.
So green, blue, and red appears similar.
And white and green appear similar. I think so. Suggest that median survival is similar for white and green flowers. And now, again, I'm going to emphasize that we adjusted our p-values. And that white and green is 0.29. So 0.29 is our p-value. And that median survival is similar for green, blue, and red flowers. So P, ADJ, and those are all, the lowest that we have is 0.4575. Okay, green. So, and here I would say is probably greater than 0.45. Rounding's off, but I took the floor of that just to say that, yeah, all of our p-values for these comparisons are greater than that. So p-adjust is greater than 0.45 for each comparison. And I think that's sufficient. think that's sufficient. So this is more probably a Mann-Whitney test, but we'll keep with it. No, Mann-Whitney, I think. I had to confirm that. We've kind of moved away from these non-parametric tests, but this is how we would do it. Now, why do I recommend not doing this? Because we're normally interested in means, not medians. So if you do the medians and you're talking about, yeah, these, mean survival is different, a reviewer is going to look at you and say, you didn't test means, you tested medians. So you kind of have to still think about how do we analyze our data if we really are interested in means. And that's going to be our topic for next week. All right? And that is that next part, which is the permutational Anova. Because, now we'll go back up here, also used, or we're going to say, this is our only option if we also violate homoscedasticity. So it's one of these things where if you violate normality, there's nothing wrong with just jumping right to a permutational Anova. You should still report if variances are equal, but there's no problem jumping right to permutational Anova, because that's going to be our only option if we violate both normality and equal variance. Likewise, if we only violated equal variance, we could run permutational Anova. That's perfectly fine, but the recommendation would have been just use Welch's because it's easy, it's preferred, or it's easy, it's well known and well known. All right. Questions? All right. Do I need to scroll down?
Can you go to the Kruskal-Wallis?
Which one? This one? This right? This part? Yeah, the Wilcoxon rank sum is also called the Mann-Whitney U-test, or it's been called the Mann-Whitney Wilcoxon rank sum test. Crazy.
Yeah, it's too short. Too much to type on.
I know.
All right.
Yeah. Well,
All right. We will have we have permutational Anovas, permutational t-tests. We've got these scripts that they're going to be up on Blackboard. We're going to use these for our permutational Anovas and pairwise permutational tests, which makes it a whole lot easier to run. But we'll introduce that on Monday, and then we'll use, we'll finish up on Wednesday. But I think we'll finish all of that on Monday, and then we've got like practice stuff, everything that in preparation for the final answer questions
our finals next week.
during finals week.
One more full week and then final.
Yeah, we've got one more full week and then finals. Yeah, I wish we would have just ended this week.
Got it over with.
Yeah, last week was pretty good. I think the benefit is with this winter term, if you do Thanksgiving, then you can kind of come back after Thanksgiving and start your winter term with the idea that you're done by Christmas.
Yeah.
And then you can have 2 or 3 weeks before the spring semester. I think there are some faculty who think that should be the way to go. It's not going to happen overnight because I know that there's other stuff that has to happen. All right. All right. Enjoy your Thanksgiving. And on Monday, we will have a practice problem where we look at turkeys. Size of turkeys in a bin at
How do
HEB.
y'all cook your turkey?
I am going to inject and then I'm going to smoke it.
I think my dad's gonna, right? Well, no, well, he did buy a new smoker, so we may